And then JJ, whenever you are ready, you can share your screen and take it away.
Okay, thank you, Jenny, for hosting this today, and thanks to the others for joining as well. So this will be pretty informal. So feel free to to um, jump in at any time if you have questions. Let me get into presentation mode. Which did I hit the wrong button? Kind of did. Let me escape out of that. Okay. Okay, so I can see my PowerPoint, but I'm not able to see any people. Can I get a, maybe from Jenny, can you see my screen in presentation mode?
Yep, everything looks great.
Everything looks good. Okay, very good. So this will be a pretty short presentation and talk about kind of a next phase of making our products, which have generally kind of focused more on the natural hazard of the meteorological forced natural hazards, and kind of moving those to the next phase into getting more at the impacts. And so we'll look at the road weather impacts, and then phase one is focusing more on flash flood related impacts. So I'd like to acknowledge my my colleagues here, and then I'll go to this slide here. So first of all, this is kind of going back, and this is probably kind of preaching the choir here, but if we know the circumstances related to fatalities from flash flooding, we see very clearly that the red bar, that they're vehicular related. So these are 61% of all flash flood fatalities are associated with vehicular related. That can occur. It's either trauma or drowning, and sadly, we saw this exact situation unfold this past weekend here in Central Region in Oklahoma. So we had 2 fatalities in Moore, Oklahoma, on Saturday evening, and then 2 more in Eastern Oklahoma, kind of south of Tulsa in the Bixby area. And we kind of did a case study yesterday in our group, and looked at the details and a little more. And I would say the Moore one was a pretty strong signal on the natural hazard side. So we looked at MRMS and some of the flash products, and there were some high values there without a doubt. So in advance of when the incident occurred, 30 minutes or so. But all that being said, the real, what pushed this into becoming just a bad situation into a fatality event is more of a kind of a human action sort of thing. So it was, I think there might have been, maybe an accident that occurred, or there has to be some reason that got them off the road and into the position they were in, because they couldn't have been really swept off the road and stuck against the culvert like we saw. But nevertheless, that's what happens. And then if we look in the eastern part of the state, we looked at that case study, and the natural hazard there was not that great. I mean, you had crest unit stream flows that were kind of in the, the moderate range, but they're encompassing, a huge part of Tulsa, part of South Tulsa, and there's no way that anybody could have pinpointed that this specific bridge. And then the family was looking to go to a friend's house, and they're driving around. They ended up on private property. They got lost, and then they drove over a bridge that didn't look like a county maintained bridge or anything. It was a terrible looking bridge, and they drove over, and there's water, and then you know what happened after that. So anyhow, those are the kind of circumstances that tend to have a lot greater influence on the human action side, and maybe less so on the natural hazard in certain cases. So that's kind of what we're dealing with, and it's a pretty challenging situation, because it forces us on the research side to think more about than just meteorology and hydrology, but get to human impacts, like what's causing this to become, a fatal incident versus just a nuisance event. And so, when you're talking about on a Saturday night, a lot of people on the roads trying to get from A to B, it's dark, we can't see what's going on, then those are the situations that can turn ugly in a heartbeat. So, and again, you all probably know this pretty well, but it's actually pretty rare to have a flash flood come and find you in your home. And that's what we have in the permanent buildings and mobile homes down here. So a large majority are people out and about in their vehicles, or they're outside, not in a vehicle, but in a known environment. That's what this OU is, outside, close to streams. And then the camping, you know, in a canyon, that kind of thing. And then the other ones are inside, you know, permanent building, mobile homes, but those are pretty rare for that to occur. And so all in all, in the US, we have about 500 people that die each year due to the weather. And this is combining all, you know, tornadoes and all the above. So about 500. But if we look on the roads, you get, you know, an order of magnitude higher than that, that are lost on the roads. And this is due to, you know, weather impacted roadways. So slick roads, could it be winter weather? Is there just, you know, wetted roadways, those kinds of things. And that causes a lot more fatalities than just the weather directly. And so if you compare that to some of these other things, the bees cause about 50 deaths per year, and deer up there pretty close to where we are with flash floods. So people hitting deer is pretty big deal. Even especially here in the kind of central U.S., it's I'm sure it's happened to everybody on the call here where you've had a close call. It's happened to me just in the last year where last second you see it and do the old swerve kind of thing. But so those happen as well. And so our lab reorganized recently. We'll see if we get the opportunity to do that again in face of the changes that are coming our way. But nevertheless, we did reorganize, and then part of that, we have 3 new branches in our laboratory. And then we have a new team within our branch, and that's what this is called, the Pathway Team. It's prediction and analysis for transportation, hydrology, winter weather, and aviation impacts. And so that is led on the Cooperative Institute side by Heather Reeves, and then I represent the federal side. And so really what we're aiming to do is to do what I said at the very beginning of the presentation, which is to move beyond just meteorology and hydrology and hydrometeorology, to shift that more to the societal impacts. And so it's really recognizing, you know, a case that Heather and I like to talk about is, you know, if we're talking about like you know, an eighth of an inch or a quarter of an inch of freezing rain, from the natural hazard perspective, you're like, you know, it's even kind of difficult to detect by radar, and you know, it's just not a very big natural hazard when you think about it just by itself. But if you superimpose that natural hazard on, let's say, a city, Oklahoma City, that's not used to having a lot of freezing rain, and it's 7 a.m. at rush hour on a Monday morning, and maybe the forecast wasn't that great and getting everybody fired up to anticipate it, then all of a sudden you can have a massive impact on the natural hazard that's really just kind of low end. But the impacts, and it could be gone, by the way, in a few hours. You know, by noon, it could be warm up and all the roads are just wet. But that impact right there can, you know, effectively shut down the schools and everybody's ability to get to work. And, you know, so that's what it's in recognition of events like that, is where the societal impacts become enormous. And they don't necessarily scale in a linear way with the natural hazard itself. So it tends to be kind of a nonlinear scaling there. So that's kind of what we're focusing on in our team. And so these are some of the products that we've worked with kind of traditionally, and these are all the ones we're going to be focusing on to move into this kind of next phase of being more impact focused. So on the left are the ones project that I've led for you know, more than a decade now, would be the flash products, which are coming out of MRMS. So I think everybody's familiar with these. And then also within the MRMS suite, on the right are more the winter weather ones, and you can find these on the dev machine that everyone has access to those as well. So that would include the freezing rain accumulation national analysis, or the FRANA, the SBC, which is kind of runs at the heart of FRANA as well, spectral bin classifier. So this is giving you the precip type. And then another one that's hasn't received as much attention, but probability of subfreezing roads, or ProbSR. So these are products that are focused more on winter weather that will then be advanced to at some point to sort of forecast when we have a winter weather situation that's going to close roads. But for now, we're focusing on the left side, which are the flash flooding and heavy rainfall products. And so we started working with MoDOT, and I saw that Scott Watson had joined the meeting here. So I want to tip my hat to him, because he's the one that made us aware of some data sets that MoDOT had in terms of road closures and signage and stuff. And it really blew my mind when I saw it. It was already in a nice GIS format, and I'll get into more of the details in a moment, but it really opened my eye, because if we want to get into predicting impacts, things like road closures due to flooding, then we're talking about using AI, ML, and then you have to have a training data set. So you need a good archive of when things close due to flooding. And it turns out that's exactly what they've got. And they've maintained a really nice archive, I think since '06, and digital archive to present, and it's a really beautiful data set. And so I think when Scott shared that with us, and it really opened our eyes, or like, wow, we can do a lot with this. This is amazing. And so, and it took some time to, to nurture a relationship and to get in contact with the people from state of Missouri with the DOT. And then one thing led to another. They do have a kind of an open season for proposals, and we crafted one. It was approved. And now it took all sorts of back and forth with lawyers, a lot of fun going on there. But eventually we did get the project funded, and we're in the early stages of it now. So that's basically what we're doing, is we're doing a pilot study so we can demonstrate the use of artificial intelligence and machine learning approaches to ultimately arrive at a statewide probability of flooded roads that are likely to be closed. So our anticipation is that this would be useful information that could then be provided to both forecasters like yourselves, but also to the DOTs, so that they could have a heads up on areas that are highly probable to be flooded, and so they can anticipate it. Maybe get crews out there in advance and start setting up signs and do what they do to close the road and rerouting traffic and do all that without, basically having to react, getting a phone call. Hey, we got water all over here. Cars are stopped and people trying to drive through it. It's a mess over here. Try to get ahead of it so that doesn't happen. So let's get into the more of the details of the MoDOT database. So again, these are all the instances of road closures that have been recorded from 2006 to present, and I'm showing them on the right. The ones in the red are all the ones that have been closed over that time period, and there's a lot of overlap, and I'll get into that in a moment. But you can kind of see areas already, like kind of the north. There's sort of a north band and this southern one, and then especially in the southeast, you can kind of see these pockets that tend to have a lot of closures in them. And there are a lot of details in this database. They have the start and the end dates of the closure. Some of these, I will admit, have some uncertainty. The end date may not have a lot of accuracy associated to it. It may be, a lot of these are like work orders, right? So it may have taken them, if it's a smaller county road, it may have taken them 3 or 4 days to get out there and to reopen it. And so, that's when they reopen. It doesn't mean it's still flooded at that time, but they do have the section and the direction, the length of the section that was flooded. And they also have an estimation of the depth. Again, MoDOT has expressed a lot of caution on using the depth, and I'll show how the data are kind of binned up here in a minute. But all in all, there are over 30,000 reports of road closures in this database. So it's way more than sufficient for what we need to do model training to start predicting a road closure. So this is looking at some of the characteristics of the variables that are coming from the database. on the left is showing the road segment length, and I put it in kilometers here. And this actually fits a really nice distribution that one would expect on a data set like this. So you see that it's that the shorter road segments are the predominant class in terms of frequency, and then you have this kind of decaying exponential sort of distribution as you get out to the longer lengths. So that to me gives a lot of credence to this particular variable, and I could understand how this goes. They're going to be pretty specific on that segment, on what is exactly closed, right? That's a detail that they're not going to estimate too much whenever they enter that in their database, because they're going to know the milepost where it's closed, and pretty specific information they need to record on that. On the other hand, if we look over here at the estimated depth of the water that's in there, and again, I'm not even sure if we'd even really use this information, but just to show what it looks like. So this looks like in weather when we look at certain things like, hail, where they tend to bin up on coin sizes and tennis balls and, things like that, where they bin up and they don't have that nice kind of a smooth distribution. And so you see they also bin up like right at 12 inches at a foot. So, half an inch, 12 foot, 18, 24, that's where you see data. And then you don't have that nice exponential decaying thing. So we probably won't use that variable much. And then we looked at the time series of the kind of monthly. So we kind of looked at the closures by month and grouped them into monthly closures, and then looked at a time series over 4 or 5 years there. And then I highlighted the month that stood out the most. So generally you do see the kind of, where we are now, April, May timeframe. That's not too surprising. I think for those of us here in Central region, that's our rainy season, right? But what was also interesting is you do see those early, winter peaks, really, right? You see 2 in February and then 1 in January. So not really not really our rainy season. So, and it's a road closure due to flooding. So, that to me suggests that there are other variables that are, creating more road flooding that's not so much just heavy rainfall driven. So in other words, is it the state of the soils? You're going to have a higher soil moisture variables during that time of year, and much less ET. So you're going to have, generally more saturated soils. Does that enable more road flooding given a lesser magnitude rainfall event? I'm not sure. So that was an interesting result, nevertheless, and something that we'll need to look into to understand the reasoning behind that. Maybe some folks can shed light whenever I get through these slides. But let's look at a couple cases here just to give you a feel for what things look like. So this is a county road, and this was a repeat offender that we like to call it. So it was closed over this time period. In 6 years, it was closed 47 times. So you're like, wow, what in the world is going on here? And so this is a highlighted segment of the road that was closed, and then you immediately see that, okay, it's a low water crossing, and it's in southeast Missouri here, for those that are familiar with the state and flooding aspects of it. And that was one of the areas I highlighted earlier. So again, you see it's a low water kind of crossing. And then we looked at some of the street view images from Google, and this is on a good day. Okay, so you see it's sunny, it's nice out, and they're driving around taking their pictures, and they didn't cross it apparently. And so this is on a normal good day, and it's got water flowing over it. So this is not surprising that this would be an issue here, given that it's a low water crossing. And I'll hopefully shed some light on how we might address something like this in terms of modeling it to be closed. And then here's another one, Logan Creek. And let's see, again, this one, here's the road closure in the red, and then it crosses the stream, as you can see. So quite similar. It's also in southeast Missouri, so a lot of similarities to the previous one, and it was a close 11 times, so not as much as the prior one. But when we look at our picture here, then there are a couple things that stand out. Again, we're on a nice day. We don't have water over the road, but there's people swimming over here. It's a swimming hole. So it is also a low water crossing that I'm sure takes water on whenever it rains. So, the threshold for flooding this thing is going to be low, but not as low as the previous one, which has, water running over it seemingly continuously. But there's another thing that jumped out to us here is if I were to zoom in a little bit, which I'm not going to be able to do, you see there's a little yellow kind of a staff gauge right there. So in other words, MoDOT has, known through experience in the past that this thing floods. Let's put some signage there so we can estimate it and see, maybe it'll notify folks like, hey, it's up to the 3, you ain't going to make it through there. Maybe it'll help deter people from trying to drive through it. And I'll come back to that in just a moment. Or actually right now. I thought it was coming a later slide, but here it is. So it turns out they've got a database, and Scott supplied these to me early on, and I looked at them. And so these are the locations of the road signs, and then I have the counts of each of them shown below each one. And these are all the ones that are related to flooding. So you have a staff gauge. That's a majority of them, 668, a little bit less than half impassable during high water, road closed, road may flood, and then water over road is a smaller percentage. But that's what they have. And this is a pretty interesting graphic here because I showed this earlier. This is the road closures, again, with a lot of overlap in there. Remember, we had, tens of thousands of road closures in here. And so a lot of these are repeat offenders. And then what I'm going to do is overlay all the road closures that have some sort of relations to flooding. Okay. And so this shows them here, and I'll kind of toggle back and forth. And I think at least subjectively, at least my eye indicates that these are pretty darn well correlated, meaning that we can utilize these information on where just the road signs are, that for whatever reason, that these are trouble spots, repeat offenders, and these are indicative of vulnerability, and we can build this into our modeling. I think it may be difficult, extremely difficult, if not impossible, to model the natural hazard. And I would like to return back to the case up in Moore, the fatality event that occurred over the weekend. And if I were to I was thinking out, with the group, with the team, like if we were to try to model this event, from the natural hazard perspective, it would require a digital elevation model that would need to be less than a meter in resolution. And I'm not even sure if it's available. It would need to be, on the order of decameters or decimeters or something like that, because just the width of the stream that pinned the car up against the culvert was less than half a lane of traffic. We're talking a stream that I could jump across on a good day. For me, not for the stream, but for me, I can literally jump across the stream, and I'm thinking, and it takes a big 90-degree turn, it's urbanized, and I'm trying to think of all the things that we would need to have to take into account to model it. And I just don't think it's doable, and probably in my lifetime, to model something at that kind of scale. And I'm trying to think, statewide and CONUS-wide, and it's just, boy, that's getting very, very difficult for models. So I do think that we can run a coarser resolution model like we do with Flash. And then if we knew details about vulnerability in these trouble spots and things like that spot right there up in Moore, I don't know if the database, like if the city of Moore they certainly knew that this was problematic in this area. And do they have that digitally stored anywhere? I don't know, but I think that might be the future of getting at these road impacts, is have some sort of information about static vulnerability, and then we can incorporate that information in a coarser resolution model. Hope that makes sense. We can talk about it more. I don't have a lot of slides left here, so we can open it up to discussion. But this is kind of the breakdown of how we're going to do our work with MoDOT. This is where we are on the left over here, is kind of building our training data set for machine learning. We looked at the temporal analysis of the closures. I showed that. There's some interesting kind of winter closure peaks that we can discuss. Looking at the spatial analysis, so we looked at clusters that tend to cluster not so much in the central part of the state, but in the north and then in the south, and a little concentrated in southwest and southeast, I would think. And then there are a lot of details that are pretty challenging that our postdoc at the moment, Jorge, will need to tackle, where you have to match the data sets. You know, you get a closure that's on this vector, like on a segment, and then we have our gridded data that comes from MRMS and Flash, and then how do we match those in space and time? So you have to create a search window, and then you have to look at some of the moments of the variables within that search window. It's a spatiotemporal window as well. So you have to extract it and figure out what's matching that little vector of closed data. And it's not an easy thing to do, but Jorge had to do this for his PhD. So I with a different database. So I think he can do it again with this one. And then we need to identify are there other vulnerability data that we can introduce. You know, we did create a database of low water crossings. It's a DEM exercise that we conducted. Will that be useful? Are there other static variables that we're missing, like the trouble spots, like I've kind of shown with the signage? That one will certainly be included in that. And then we start getting into the development of the model itself, and this is where Jorge got his PhD in industrial and systems engineering, so I trust that he'll be able to work these details out. And then lastly, this is what we'll get to, is more of a demonstration system, which would be a probability of road closures due to flooding will be kind of what the product will look like. So it'll be I don't know if I haven't even really begun to think of, will this be on a grid? Will it be on the MRMS grid? And we'll just highlight, road sections that kind of the grids that overlay roads, or can we just go to a vector kind of approach and do actual vectors that we think would be closed? So haven't gotten that far yet. And this is kind of a more of an illustration of what this whole model would look like for predicting flooded roadways. So we have our static data up top. So this would be vulnerability, any static information about what may cause a road to flood that's available digitally, and we would incorporate that information. I'd certainly welcome inputs on additional variables that might inform that process. In dynamic data, presently, we're going to start with MRMS and Flash outputs. As time goes on, we want to improve our predictability and our lead time, and that's where we would consider other inputs that could come from, QPF ensembles. So we could incorporate just about anything into that, with the understanding that you're going to have more uncertainty due to the temporal and spatial offsets of where the precip is. And we do have some, hopefully, if things move on as we hope they will, then we do have some efforts underway to basically couple warn-on forecast system ensembles to Flash. And so that would be a natural integrator into this system, because then that'll enable us to just add on about 6 hours of lead time. And there, I'm pretty confident that the ensemble that warn-on forecast produces encompasses the true uncertainty in terms of where the spatial precipitation patterns are going to be. I don't feel that way with other ensembles. When you move out to more than 12-hour forecasts, they're just kind of throwing precip here and there, and you almost have to draw a big contour around that and hope for the best. But in any case, then we get into the training. That's where the closure data comes in at the bottom. And then we do our training, and that's a big, heavy, we'll be using GPUs for that. And that's a big lift, computationally speaking. But once that's done and you have your model, it's extremely efficient. So you can run it very, very fast and then be able to get to the ride. Here we're showing kind of what it might look like over on the ride, is showing these kind of flash flood warning polygons that we have now. And then within that, you may have a lot more detail about where roads are could be inundated due to flooding. So to summarize is hopefully one of the big take-home messages with where we're moving is the magnitude of the natural hazard doesn't always scale in a linear way with the severity of the impacts. So sometimes the impacts become really severe with not that great of a natural hazard. I think flash flooding and winter weather are both pretty good candidates for that. And then large data sets like the MoDOT road closures can have great value for training and then eventually get to impact-based forecasting. And then additional information. I think the key to make these succeed is we got to have information about the vulnerability aspects, like the road signage, low water crossings, any other things. Could be flood inundation maps, could help inform these models, and then we can get to the specific impact. So presently, our project with MoDOT is still in the early stages. We just reported on first quarter progress with that. And in our entire first year is focused on flooding. And then ultimately, we want to use this exact same framework that we're building, but then shift the focus to winter weather impacts, because we know those are a big deal as well. So I think that's where we are right now, and I'll just go ahead and stop there and be happy to take any questions and suggestions, comments, improvements. We're early in this work, so we can certainly integrate inputs, and we welcome them. And yeah, I'll just stop there.
Awesome. Thanks so much, JJ. That was fantastic. A lot of really good examples there too. If you do have questions, feel free to type it in the chat, raise your hand, or just unmute yourself. And for those that weren't able to join right at the beginning, this is recorded, so we will be able to distribute this probably in the next couple days, and we'll post that on our website. And I'll have Stephanie Cipral email that out as well to the group she sent it out to. Any questions? All right. If not, that concludes today's Innovation Spotlight. Thank you so much, JJ, again for presenting to us, and we will see you back next week. Thanks, everyone.